Hi, sir. This is T. Kushi from IDA, and my roll number is 37. And my topic for concept video for the subject discrete mathematical structures is rules of inference. So, coming to the rules of inference, simple arguments can be used as building blocks to construct more complicated valid arguments. Certain simple arguments that have been established as a valid are very important in terms of their usage. Inference rules are the templates for generating valid arguments. Inference rules are applied to derive proofs in artificial intelligence, and the proof is a sequence of conclusion that leads to the desired goal. So, inference rules are nothing but these are set of arguments or instructions or templates. These are generally used in artificial intelligence. So you will prove a particular statement with the help of few steps. So proving a particular statement in the form of steps and coming to a conclusion to lead a desired goal is called as rules of inference. In inference rules, the implication among all the connectives plays an important role. Following are some terminologies related to inference rules. So first is implication. It is one of the logical connectivities which can be represented as P implies Q, and it is a Boolean expression. Converse. The converse of implication, which means the right hand side proposition goes to the left hand side and vice versa. So it can be written as Q implies P. Contrapositive. The negation of converse is termed as contrapositive, and it can be represented as negation Q implies negation P. Coming to inverse, the negation of implication is called inverse. It can be represented as negation P implies negation Q. So, some of the important terminologies of inference are implication, converse, contrapositive, and inverse. Implication is nothing but P implies Q, converse is Q implies P, contrapositive is negation Q implies negation P, and inverse is negation P implies negation Q. So, from the above term, some of the compound statements are equivalent to each other, which can be proven using the truth table. So you're going to take a truth table. So it is having two variables, P and Q. So you will get four outputs. So P and Q. So the four conditions are true, 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 false, false, true, and false, false. So when P and Q are true, then P implies Q becomes true. Q implies P also becomes true. Negation Q implies negation P also becomes true. Negation P implies negation Q also becomes true. Coming to true false, when P is true and Q is false, P implies Q, negation Q implies negation P becomes false, and Q implies P and negation P implies negation Q becomes true. So in the same way, you will find it for false true and false false conditions. Hence, from the above two table, we can prove that P implies Q is equivalent to negation Q implies negation P, and Q implies P is equivalent to negation P implies negation Q. The most commonly used rules of inference are tabulated below. So first is that first rule is modus ponens rule. Here you are going to take a P comma P implies Q. So P comma P implies Q can be written as Q. So in tautology you can represent as P and P implies Q implies Q. Next is modus tollens. Modus tollens is nothing but negation Q, and P implies Q is equivalent to negation P. Next is hypothetical syllogism, that is P implies Q and Q implies R gives you P implies R. Next is disjunctive syllogism. So here negation P and P or Q gives you Q. Next is addition, that is P can be written as P or Q. Next is exportation. Here P and Q implies R, and that is P implies Q and R. Next is resolution. Resolution is P or Q, comma negation P or Q is nothing but Q or R. So these are some of the rules of inference. So these are modus ponens, modus tollens, hypothetical syllogism, disjunctive syllogism, addition, exportation, and resolution. Similarly, we have rules of interface for quantized statements. So you have two types of quantized statements, that is universal quantization, quantification, quantifiers, and existential quantifiers. So universal quantifiers are generally denoted as for all, and existential quantifiers are denoted by as there exists of. So first is instantiation, universal initiation. So for all p of x, you can write it as p of c, and universal generalization, p of c for any arbitrary c can be written as for all p of x. Next is existential initialization. So there exists p of x can be written as p of c for some c, and in existential generalization, p of c for some c can be written as there exists x p of x. So, four types of quantifiers we have. These are also included in rules of inference, that are universal instantiation, universal generalization, existential initiation, and existential generalization. So, types of inference rules. So, now we'll discuss them in a detailed way. The Modus-Penaz rule is one of the most important rules of inference, and it states that if P and P implies Q is true, then we can infer that Q will also be true. So it can be represented as P implies Q, comma P is nothing but Q. So let us take an example. The first statement is if I am sleepy, then I go to bed. So P implies Q. This is statement 2 is I am sleepy, that is Q, and conclusion is I go to bed, Q. Hence, we can say that if P implies Q is true and P is true, then Q will automatically be true. So proof by giving the truth table. So we are going to take again two values, that is P and Q. So you'll have four outcomes or four conditions. If P and Q are 0, then P implies Q is also 0. If P is 0 and Q is 1, then P implies Q is 1. If P is 1 and Q is 0, then P implies Q is 0. If P is 1 and Q is 1, then P implies Q is also 1. Next is modus tollens. The modus tollens rule states that if P implies Q is true and negation Q is true, then negation P will also be true. So it can be represented as P implies Q, comma negation Q can always be written as negation P. So now let us take another example. If I am sleepy, then I go to bed. I do not go to bed, that is negation Q. And if I am sleepy, then I go to bed is P implies Q, which infers that I am not sleepy, that is negation P. Next is hypothetical syllogism. So the hypothetical syllogism rule states that if P implies R is true, whenever P implies Q is true, then automatically Q implies R is also true. So it can be represented as the following notation. So let us go through an example again. So first statement is if you have my home key, then you can unlock my home. That is P implies Q. If you can unlock my home, then you can take my money. That is Q implies R. So if you have my home key, then you can take my money. That is P implies R. So this is the example. That is P implies Q, comma Q implies R gives you P implies R. So this is the truth table. So here you're going to have P, Q, R. That means three variables. So you're going to get completely 8 combinations. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So these are your 8 combinations. And you will get the outputs for these 8 combinations. So if P, Q, R are 0, then P implies Q is 1, Q implies R is 1, and P implies R is also 1. So in the same way, you will be doing for each and every circuit. I mean, each and every combination. So next one is disjunctive syllogism. The disjunctive syllogism rule states that if P or Q is true and negation P is true, then Q will automatically be true. So here in the notation, you can write as P or Q, comma negation P can be written as Q. So coming to the example, first statement is today is Sunday or Monday. So P or Q. Second statement is today is not Sunday. So that is negation P. Conclusion is today is Monday. So P or Q, comma negation P always gives you Q. The fifth thing is addition. The addition rule is one of the common inference rule, and it states that if P is true, then P or Q will also be true. So let us take an example. So statement 1, I have a vanilla ice cream, that is P. Statement 2 is I have a chocolate ice cream. I have vanilla or chocolate ice cream. So P can always be written as P or Q. Next is simplification. The simplification rule states that if P or Q is true, then Q or P will also be true. It can be represented as P and Q can be written as Q, or P and Q can also be written as P. So let us see the proof using the truth table. So here again you are having P and Q, that is two variables. So you will get 4 combinations again as usual. So when P and Q are 0, then P and Q will also be 0. If P is 1 and Q is 0, then also P and Q is 0. If P is 0 and Q is 1, then also P and Q value is 0. And if P is 1 and Q is 1, then P and Q value is 1. Coming to the resolution, the resolution rule states that if P or Q and negation P and R is true, then Q or R will also be true. It can be represented as follows. So notation P or Q, comma negation P and R, then these two equations can be written as Q or R. So let us prove it by using the truth table. So here you are going to get 3 variables, that is P, Q, R. So you are going to get 8 combinations again. So when it is 0, 0, when P, Q, R are 0, then P or Q becomes 0. Negation P and R becomes 0, and Q and R also becomes 0. When P is 0, Q is 0 and R is 1, then P or Q becomes 0. Negation P and R becomes 0, and Q or R becomes 1. When P is 0, Q is 1 and R is 0, then P or Q becomes 1. Negation P and R becomes 1, and Q and R also becomes 1. When P is 0, Q is 1 and R is also 1, then all the 3 conditions will also be 1. When P is 1 and Q is 0 and R is 0, then P or Q is 1 and rest 2 conditions are 0. When P is 1 and Q is 0 and R is 1, then P or Q is 1, negation P and R is 0, and Q or R is 1. When P is 1, Q is 1 and R is 0, then P or Q and Q or R is 1 and negation P and R is 0. When P is 1, Q is 1, R is 1, then P or Q, Q or R are 1 and negation P and R are 0. So now let us go through an example. Show that the hypothesis, it is not sunny this afternoon and it is colder than yesterday. We will go swimming only if it is sunny. If we do not go swimming, then we will take a canopy trip. And if we take a canopy trip, then we will become home. Then we'll be home by sunset. Lead to the conclusion we will be home by sunset. So the first step is to identify propositions and use propositional variables to represent them. So P represents it is sunny this afternoon. Q represents it is colder than yesterday. R represents we will go swimming. And S will represent we will take a canopy trip. And T will represent we will be home by the sunset. So let us take the first statement. It is not sunny this afternoon. And it is colder than yesterday. So the first proposition is that it is not sunny. Negation P and Q. So the first proposition is negation P and Q. Next, we will go swimming only if it is sunny. So we will go swimming is represented by R. R implies P. That is second proposition. And the third proposition is that if we do not go swimming, that is negation R, then we will take a canopy trip. So negation R implies S. So this is our third proposition. And the fourth proposition is that if we take a canopy trip, that is S, then we'll reach home by sunset. So S implies T. So the four propositions are negation P and Q, R implies P, negation R implies S, and S implies T. So these are the four propositions, and the conclusion should be negation T. That is nothing but we will be home by sunset. So to deduce the conclusion, we must use rules of inference to construct. So first step, we are going to consider one proposition, that is negation P or Q. And the next one is you are going to take negation P. So by simplification formula, uh, in the form, when you simplify the first equation, you will get it as negation P. Next, take another hypothesis, that is R implies P. So when you apply modus tollens use on second and third statements, you will get negation R. So that will be a fourth statement. Now take the another hypothesis, negation R implies negation S. So use modus ponens, that is P implies Q, P comma P implies Q is Q. So you will apply modus ponens on equation 4 and 5. So you will get, so negation R comma negation R implies S becomes S. Now again take the last hypothesis, that is S implies T. Now again apply modus ponens on 6th and 7th equation. So S comma S implies T gives you T. So according to the question, what should our conclusion is nothing but we will be home by sunset. That is nothing but represented using alphabet T. So we got the conclusion T. So this is how you use inference rules and derive a particular hypothesis. Hope you guys understood this. So you have many types of inference rules, that is addition rules, simplification rules, modus ponens, modus tollens, resolution rules, disjunctive syllogism, conjunctive syllogism, simplification, etc. And you also have quantifiers, that is universal quantification, universal generalization, and existential quantification and existential generalization. So in existential, you will use there exists of, and for I mean universal quantifiers, you're going to use for all x belongs to. So using all these rules of inference, you're going to solve a given example or given hypothesis. So let us have a quick revision of all these important rules of inference from the table which was already mentioned before. So from this table, modus ponens means P comma P implies Q is Q. Modus tollens means negation Q comma P implies Q is negation P. And hypothetical syllogism means P implies Q comma Q implies R as P implies R. And disjunctive syllogism means negation P comma P or Q is Q. And addition means P can be written as P or Q. And resolution is nothing but P or Q comma negation P or R is nothing but Q or R. And next is for the quantifiers. For all x p of x, that can be written as p of c, and p of c can be written as for all x p of x. And there exists p of x can be written as p of c for some c, and p of c for some c can be written as there exists p of x. So these are the important formulas. So using these formulas, you are going to solve the examples using separate hypothesis. You are going to derive a particular conclusion. Hope you understood the rules of inference and hope you understood the examples. Thank you so much.